we were talking about molecular compounds. And this list is actually a big list of molecular compounds. Actually, this is not. This is a different list, and shame on me for saying that. But this list is a list of molecular compounds. And these are, and what we did first is we asked you to look at what elements made up molecular compounds. So in order to do this, we have N, O, S, Cl, I, F, B, and that's pretty much all of them, right? So let's take a look at the periodic table. So we have, if we're keeping track, we have N, O, F, Cl, I, B was in here, right? And C, I think, was also there, right? If we kept on going with this and we looked at all of the problems that we did in the homework, you'd also find P and S and SE were also, and I believe KR and XE were used in these homework problems. And so what you see is everything basically to the right of this zigzag line right here, right, are going to be bonding covalently or in molecular compounds. And so what I like to think of them as this is all of the all of the nonmetals and the metalloids, right? So if we look at this, nonmetals, right, and metalloids, right? We don't usually make a big deal about that, but metalloids also bond covalently, right? So nonmetals and metalloids are going to be the elements we're playing with. Now, if you wondered why, because if you recall, if we look at this in Unit 5, we said every compound in Unit 5 had the section from this set of the part of the periodic table, the metals, right? And these guys lost electrons, they lose electrons, and they form cations, positive cations, right? Right. Whereas the guys on this side of the table, right, they gain electrons, right, and they form negative anions, okay? And so we had a cation and an anion, and we said, okay, that makes sense, right? Because we have the negative attracting the positive, and that just makes good common sense. However, it turns out that these nonmetals that gain electrons can actually attract each other, but they do it in a slightly different way. Instead of gaining electrons and losing electrons and then being attracted by opposite charges, what happens is two of the same type of atom can attract each other by being attracted to a common pair of electrons. Okay? And so if you look at this, what ends up happening is you'll have something like Cl, right? And Cl has electrons of its own, but it's also attracted to extra electrons. And this other Cl will be attracted to that same set. And so if there's an attraction between this Cl and those electrons and this Cl and those electrons, then the Cls don't have to be attracted to each other, right, to be bonded. They're bonded because of their mutual attraction to this pair of electrons that's in between them, right? And so because this chlorine is unwilling to leave this pair of electrons and this chlorine is unwilling to leave this pair of electrons, they stay bonded to each other as a unit, okay? And so it's not like being attracted because they're opposites. It's like they're attracted to the same thing in between them. Okay? So we're going to be talking about this sharing of electrons, this covalent bond, and we're going to see how it shows up in molecules. Right? So if we look at these things, the first thing we wanted to do is we wanted to look at how to name them. And this compound here is N2O3. Well, we know that the 2 means that you have like 2 nitrogens, right? 2 nitrogens. And we have 3 oxygens. And that looks pretty clear, right? 2 nitrogens, 3 oxygens. Well, instead of writing it this way, what we're going to do is we're going to use these Greek prefixes. We have a list of them right here, these Greek prefixes: mono, di, tri, tetra, etc. And so in this case, 2 is di and 3 is tri. And you might actually know this from different places. Like tri, you might think of a triangle, right? Or you might think of, I don't know, a three-wheeled thing that you rode when you were a little kid, right? You know, right, with the little handlebars. You might think of a tricycle, right? Right. A die, I always, when I was a kid, remember die because when you played board games, you had a pair of cubes, right? And those cubes had little dots on them. Possibly I'm telling you things you already know, right? So you had whatever they are, dice, right? Right, so you had these dice, and dice, if you have 2 of them, right? Yeah, it starts with die, and it reminds you that die is 2. I don't think that actually dice comes from the prefix die, but it might. And either way, that's how I remembered it. So you need a story for yourself to remember these things. That will help you. Tetra is a tough one for most people, but you guys who play cheesy video games might remember that there's a game that involves a bunch of shapes all made with 4 blocks. And that, right? So we have 4 blocks making up these various shapes, right? And they all fall down, and you have Tetris, right? And Tetris, right, is from that same root, 4. Tetris, right? Tetra. 1, 2, 3, 4, right? And so forth, right? So they all have 4 blocks. And penta, you might know from Pentagon, right? You know, the military building. Or Pentagon, the geometry shape, right? So these are the same prefixes, in fact, you use for bigger shapes in geometry as well. So you need some way of remembering all of these shapes, all of these prefixes, okay? But anyway, we're going to use one down below. So if we take a look at this, 2 nitrogens, 3 oxygens becomes di, nitrogen, tri, oxide. Okay? And so that's its formal name. 2 nitrogens, 3 oxygens becomes dinitrogen trioxide. And we'll set up these rules a little more formally. So if we go over here, the first rule is we use the Greek prefixes. Oops, let's actually make this a proper noun. To identify the quantity of each element. Right? So that's pretty simple. Di, tri, right? The Greek prefixes. The second thing is that we use the second element always ends in "ide," right? We put the more electropositive right? We end it with "ide," right? That's because we're treating it kind of like an anion. And if you'll recall from the last unit, right, monoatomic anions always end in "ide." So chloride is Cl minus, oxide is O2 minus, sulfide is S2 minus, and so forth. So we're treating that second element as if it's an anion and it ends in "ide." And then last but not least, we only use mono if it applies to the second element, right? Right. It's treated as if it's understood on the first element. Okay. So let's take a look at how this works. If we take a look at this guy here, right, we have 1 sulfur and 2 chlorines, right? So basically we have 1 sulfur and 2 chlorines, and so it's going to be mono, if you will, sulfur dichloride. All right, except that we drop the mono on the first one, and so it just becomes sulfur dichloride. Okay, so there it is. 1 sulfur, 2 chlorides becomes sulfur dichloride. Okay, and so that's how we do the naming. But we can work backwards and do the formula as well. If you look at this one, phosphorus trifluoride, there's nothing written here. So this must be our understood mono, right? So this is monophosphorus, so 1 phosphorus, trifluoride, 3 fluorines, right? And so we can work backwards, right? And if we write this as a chemical formula, that's PF3. Okay, and there it is. That's the way we deal with formulas. If we wanted to deal with one that is, I don't know, a little bit different. Here's chlorine monoxide, right? Chlorine monoxide. And here you have the understood mono here and also the mono here. So this is like 1 chlorine and 1 oxygen. So it would be like ClO. Not certain that chlorine monoxide actually exists, but if it did, it would be ClO. Okay. And let's make that a 1-looking 1. Let's say 1-looking 1. So you'd see that that's Cl and not C1. Right? Yay us. A couple things before we finish, and that is there are these notes here. A molecular compound or covalent compound is a group of atoms, right? And they're joined together by covalent bonds, which makes sense because they're covalent compounds. It's kind of a tautology. A covalent bond forms when atoms share. And this is the thing I was talking about before, that covalent bonds are always talking about sharing some common pair of electrons, right? And if you actually look at the term covalent, right, the co implies that the valence electrons are being shared, right? Share valence electrons. Okay, so covalent, like 2 people sharing, right? Share valence electrons in order to have a full valence shell. Now, they probably don't care whether they have a full valence shell, but they can't have more than a valence shell, and they can't, and right, so nonmetals are going to attract electrons. They will keep on attracting them until their valence shell is filled. At that point, new electrons would have to go in an outer shell, and they would be repelled by all those electrons you've already added. So we always end with a full valence shell. Now, a full valence shell means that the s and p blocks are full. So if you had the second energy level full, you'd have 2s2, 2p6. If you had the third energy level filled, you'd have 3s2 and 3p6, right? Well, that means those outer electrons are always 8 total, right? A full valence shell is 8 total electrons, right? 2 plus 6, 2 plus 6. And so we're going to call it the octet rule. Octet rule, right? Because 8 is an octet, right? So it's an octet. Molecular compounds are composed of 2 or more nonmetals or metalloids. Right? But let's not talk about the metalloids too much. So there it is. That is everything we did on Tuesday. I hope that this has been helpful, and you should, at this point, be able to do the last 2 problem sets in the packet.